All right, we are now recording. All right, let's go ahead and get that up and ready to go. All right, come on. There is, oops, maybe I should actually share the screen. Wouldn't that be helpful? Share every freaking time. I don't know why that's Zoom's default, but when you decide to share the screen, it just overrides any of the decisions you had made about system sound and system microphones, etc. All right. And where's our chat box? Perfect. Cool. So, last time you had your exam, this isn't working. I don't know if I did post them or not. So let me quickly post them while I'm just going over the exam statistics. So the average score for this exam was a 70%. That was a little lower than ideal, but that largely derives from the substantial variance in the data. There was a substantial negative skew while I'm getting this up and posted. I will try to remember everything, but I think there were 6 perfect scores on the exam. And all right, about half the class got an A or a B on the exam. Hold up, gotta see. Oh, that's gross. Now I've got that in my mask for the entire class. Awesome. All right. We're not going to go over the specifics of the exam because a couple of your classmates still have yet to take the exam for a variety of valid reasons. And so we won't go over any of the specifics, but again, a reminder that you get to drop your lowest exam grade of the exams you've already taken. You do not, I repeat, do not get to drop your final exam. Everybody has to take the final exam. So please don't at any point, we've gone over this a couple times this semester, think that you don't have to take the final exam. Everybody has to take the final exam, regardless of how well you've done on the previous exams. All right, Kenya, that should now be uploadable. Kenya and everybody, that should now be uploaded. All right, get that uploaded. And now let's get that chat box back. Cool. All right, so like I said, the average score is about a 70%, 6 perfect scores. That average is brought down a little bit by a handful of people who I think opened the test and then decided this was going to be the test they dropped and just stopped taking it. So there you go. We're going to skip that because what we learned last time is for exam taking stuff. Any general questions about the class or the final exam, etc.? Yeah, Andrew.
So,
Sure, I'll come to you in just a second, Kate. Yes, so last week is our last in-class class. Yes, next week.
You said last week.
Yes, yeah, you're not here right now. Don't, yeah, none of this is real. No, next week is our last in class. And I have to look at the syllabus, but I think we have Thanksgiving. We come back from Thanksgiving, and I think we have 1 week of classes, or yeah, nothing for Thanksgiving week. The first week of December, I think, is our last week of class. That will be fully online, and that will only be review sessions. So yeah, look at the syllabus to double check, but I'm almost positive that that will be all. So final exam, yes. Thank you, Kyla. Should be Monday, December 7th. That information is all available on UH's registrar website, but I'm almost positive that's right. All right, Kate, you had a question?
Yes, will the exam be all new stuff, or will it be a mix of all the exams we've had?
It'll be a mix of all the exams we had. So we'll have 3 new lectures into that final exam. So there will be quizzes on that, but then it will probably be 3/4 old stuff. So yeah, Julie.
Are you going to put mean square error on the exam? And if you are, can you please go over and do that again?
Not today, but I can during the review sessions. Yes. All right. Any other questions? All right. Awesome. Here's your fun fact of the day. Lobsters have bladders on either side of their head, so they communicate by urinating at each other. If they want another lobster to know whether they're happy, sad, or angry, or even interested in a relationship, they say it with pee. It is kind of gross. So I've got 2 dogs, as I illustrated the first day of class. And the male dog pees with reckless abandon, and the female dog likes to have her head down and sniff. And there have been a good number of times where he's peed on her head. Yeah, it's not ideal. We rushed her to the shower thereafter because I don't want to deal with that crap. So, what's that?
My dog peed on my cat once.
It's gross. Gross.
Yeah.
All right. So, Amanda, I assume that's in response to the fun fact of the day and not something I said about the final exam. But if it's about the final exam, we can talk later. All right. Excuse me. So to this point, I have discussed what we call parametric statistics, right? And I've highlighted this distinction between parametric and non-parametric statistics to this before today. But the term non-parametric refers to the fact that chi-square tests, the test we're going to be covering today, do not have assumptions about the population parameters, nor are they testing hypotheses about the population parameters, right? So we had some assumptions when we went into things like ANOVAs and t-tests. Can anybody remember what one of those assumptions was?
That it was a normal distribution?
Exactly, yeah, that we're pulling from a normal distribution. Sorry, I had lunch right before here, and my throat is nice and scratchy. So yeah, that it's a normal distribution, which is to say that we're pulling from a distribution that didn't work, that looks like a bell curve, right? And when we're pulling from a distribution that does not look like a bell curve, so it does not look like this, right? Maybe it has a skew, maybe it's uniform distribution. We violated that assumption, and thus we should not be running that parametric statistic. Non-parametric statistics are used for when we either violate that assumption or when we're using data that wouldn't work in an ANOVA or a t-test, right? So frequency data isn't going to work. If I count the number of times I flip a coin heads and count the number of times I flip a coin tails, you can't use that in that data because you've only then essentially got 2 data points, right? One for heads, one for tails. So everything we've done up to this point, the t-test, the ANOVA, those are parametric statistics. And if you understand this distinction between parametric and non-parametric, you will be the smartest person at most cocktail parties, or at least be able to fake it. So the most obvious difference between the chi-square tests and the other hypotheses we've considered is the nature of the data, right? And so I just kind of previewed this. So for chi-square, we're using frequencies rather than numerical scores. So aside from coin flips, somebody give me an example of a type of research study for which the data we collect would be frequencies rather than numerical values.
Rolling a dice.
Yeah, rolling a dice, people's favorite colors, types of cookies grabbed, etc. And so we have two different chi-square tests that we're going to be covering today. The goodness of fit test and the test of independence. So the chi-square test for goodness of fit uses frequency data from a sample to test hypotheses about the shape or proportions of a population. And because we're using frequencies, every participant is classified into one category on that scale of measurement. All right, so UAH, UAB, and UA Tuscaloosa. Favorite colors on the Roy G. Biv spectrum, etc. Now we're going to differentiate between observed frequencies and expected frequencies. So observed frequencies are our actual counts, right? So how many times did that coin come up heads? How many times did it come up tails? The expected frequencies that we'll go over are essentially going to be either what's the null hypothesis, or given our data, we can calculate what the expected frequency would be for every individual cell. So for the goodness of fit test, the null hypothesis is what's specifying the proportion of the population that would be in each individual cell. Right, so if we're flipping a coin, what's the proportion that we would expect heads and what's the proportion that we would expect tails? Half and half, right? 50% heads, 50% tails. If we're doing it for rolling a regular die, it would be 1/6 coming up 1, 1/6 coming up 2, 1/6 coming up 3, etc. So the proportions from the null hypothesis are used to calculate or compute those expected frequencies that describe how the sample would appear in perfect agreement with the null hypothesis. Right, so if this is not a loaded dice, right, it's not likely to come up with a certain number, we would expect, on average, about a 16% chance of any individual number coming up. So let's look at the data. Right? Let's say we collected eye color for everybody in this class. And what we found is that 12 people had blue eyes, 21 had brown eyes, 3 people had green eyes, and then we had other for 4. And what we want to know is there a significant difference between eye color for people in this class? Right? Are these equally likely, or do we have distortions in the data such that when we're looking at it, it appears there are more brown eyes in the class. But we have to see whether or not that is a statistically significant difference. Questions so far? Yeah.
So is the null hypothesis always that there's an equal distribution in categories?
It's frequently that there's an equal distribution. You could, in theory, have some null hypotheses that would represent unequal distributions. You know, I don't remember the exact population breakdown, but I think humanity, by and large, is something like 52% female.
Yeah.
And so if you were looking at, okay, are there more women than men or men than women in a certain career field, your null hypothesis would pull from that and say, okay, there's 52% female and 48% male as those expected frequencies.
You can have something that you're comparing it to that's not, technically evenly divided.
Yeah. Mm-hmm. Exactly. So the second chi-square test, and we're going to go over examples for each one of these, is what we call the chi-square test for independence. The most patriotic of all the tests. It can be used and interpreted in two different ways. First, testing hypotheses about the relationship between two variables in a population. Or two, testing hypotheses about differences between proportions for two or more populations. And although the two versions for the test for independence appear to be different, they're equivalent and interchangeable. That first version of the test emphasizes the relationship between chi-square and a correlation because both procedures examine the relationship between two variables. The second version of the test emphasizes the relationship between chi-square and an independent measures t-test, or ANOVA, because both tests use data from two or more samples to test the hypothesis about the difference between two or more populations. All right, so a chi-square test for independence would be, is there a difference between eye color if we're looking at both UAH and UAB, right? So now we want to see, is there a uniform distribution of eye color in general? Is there an interaction between UAH and UAB on those eye colors, excuse me. Right? So whereas a goodness of fit is just looking at essentially one variable, heads or tails, rolling a die 1 through 6. Test for independence is looking at those potential interactions. So the first version of chi-square test for independence used data as one sample in which each individual is classified on two different variables. I think this will all make a little bit more sense when we actually pull up the data here. And we're usually presenting that in a matrix with the categories for one variable defining the rows and categories for the second variable defining the columns. So if I had color of eyes, so blue, brown, green, and then I had UAH, UAB, and now I get frequencies across these. Does the difference between these two types of tests make sense? Questions about these two different types of tests?
I have a question.
Yeah, Kate, what's up?
Okay, so what did you say an example with eye colors was for the goodness of fit?
So for the goodness of fit, it would just be as if we didn't have the second variable, right? So if we go back to this example, so goodness of fit would be just one essentially variable or one factor with different categories, right? And so this would be all the eye color. Another example would be heads versus tails on a coin flip. Another example would be 1 versus 2 versus 3, etc. versus 6 for rolling a die. But it's only one variable, right? It's only one thing of interest with different categories for that. Does that make sense?
So you can see goodness of fit as like a 1 factor and independent as like a 2 factor?
Yeah, exactly.
Okay, thank you.
Can someone tell him that he's muted?
Can you hear us?
Dr. T, we can't hear you.
Did you ever figure out what was happening with the hearts and stars thing?
I did.
What was it?
Somebody in class.
Oh.
Yes. Can y'all hear me? Okay, awesome. I don't remember what I was just talking about. Somebody asked a question, I think.
Frequencies. Yeah, so chi-squares are regarding frequencies, and the ones that
Yes.
are.
Yes, exactly. So yeah, we one example of what we would have done before would be things like, so if we got the weight of everybody in class, and that would be a numerical value, right? Every participant has its own numerical value, whereas for categorical variables, so like class year, like eye color, right-handed versus left-handed, we could only have actual frequency evaluations, right? Everybody's either yes or no, rather than having a numerical value for participant. Does that make sense?
Is it nominal then?
Yes, yeah. And you could also use cases of ordinal, right? If you were looking at, well, let's just stick with the extremes. Yes, nominal is kind of where its bread and butter is. All right. So, for whatever reason, when it kicked me off Wi-Fi, it also kicked me off of that screen share. So give me 1 second here. Let me get it re-uploaded. Working. All right, there we go. Hot damn, we're at it again. Yeah, so by and large, we are using chi-square tests predominantly for nominal data that is, in fact, these different frequencies, these categories. You will find examples where that is not the case, but for purposes of this class, that will always be the case. All right, so like I said, the data we collect in these we call the observed frequencies, showing how many individuals from the sample are in each cell of that matrix we created. The null hypothesis in this case says there's no relationship between the variables, and the two variables are independent. Hence, test for independence. The second version of that test for independence uses the data as two or more separate samples representing different populations being compared. So this would be representative of the eye color by UAH versus UAB, right? We have two different populations in that case, rather than looking at the independence of the variables. The same variable is measured for each sample by classifying individual subjects into categories of the variable. And as we've already gone over, we present those data in a matrix with the different samples, defining the rows, and the categories, defining the columns. Right, so in that example I had earlier of blue versus brown versus green, and UAH versus UAB. The different samples we have are right here, defining those rows, and then the categories are representing those columns. So again, just reiterating that null hypothesis for this test states the proportion, the distribution across categories, are the same for all populations. All right, so both chi-square tests use the same statistic and thus require the same two steps. We first calculate our idealized sample distribution of expected frequencies. And we'll go over actually how to do that in just a minute. That describes how the sample would look if the data were in perfect agreement with the null hypothesis. So again, a coin flip, we would expect a 50-50 distribution. If we flipped a coin 50 times, we would expect 25 heads, 25 tails, right? That would be in perfect agreement with that null hypothesis. And so to get those expected frequencies depends on which test we're running. Goodness of fit versus test for independence. For the goodness of fit test, the expected frequency for every category is obtained by P times N, wherein P is just the proportion or the probability, and N is the size of that sample. Right? So again, if we have heads and tails, we expect 0.5 heads, 0.5 tails. So if we do 200 coin flips, the expected frequency for heads would be 0.5 times 200. So that'd be 100. And then for tails, it again would be 0.5 times 200, which would give you 100. What would that probability be, or proportion be, if we were talking about rolling a die? So we're just talking about the probability here, or the proportion. So not the n. Yeah, so 1 out of 6, exactly. So if I rolled a dice 60 times, the null hypothesis in this case would suggest that the expected frequency for every individual number should be what?
10.
Yeah, 10, exactly. 1/6 times 60, every individual number should come up 10 times. For the test of independence, that expected frequency for each cell in the matrix is obtained slightly differently. We're multiplying the row total for that cell and the column total for that cell and dividing by n. So we'll do this in just a second here. All right. So, crap. In this case, our n is going to be the total number of observations, which in this case is 200, right? If you were to add up each one of these 6 cells together, you would get 200. You can also make it easier on yourself by adding the totals for the rows or the totals for the columns. Don't add them all up, but your n is 200. And so let's go ahead and find the expected frequency for each individual cell. So to find the expected frequency for this cell, what do I do?
Take the row total and then the column total, multiply them together and divide them by.
Okay.
n.
Yeah. So I'm doing 80 times 40 over 200.
I'm still confused how you got n is 200.
That's just the number of observations we have, right? So if this is, we're looking at what people's preference is for a vehicle, right? And so the number of people who say performance is most important, the number of people who say reliability is most important, the number of people who say style is most important. And then we have male and female. We had 200 people when you add up these 6 cells here, right? So 21 plus
I see
33
what I
plus,
did wrong. I added the totals too.
yes, don't add the totals. Good
I
catch.
just looked down and saw 3, 3, 3. Yeah, okay, I get it. Thanks.
Of course. All right, so if we do 80 times 40, me pull up my calculator here. 80 times 40 divided by 200 gives us 16. So our expected value in this case for that cell is 16. So we'll do the next one, we'll do the female here. So 40 times 120 divided by 200 gives us 24 for expected frequency. Moving over to reliability for males, 100 times 80, 8,000 divided by 200 gives us an expected frequency of 40. For reliability for females, 100 times 120, 12,000 divided by 200 gives us expected frequency of 60. Over to style, we're doing 80 times 60 divided by 200 gives us an expected frequency of 24. And then last one, female for style, 60 times 120 divided by 200 gives us 36. Questions on how we did that? Yeah. I'm sorry, one more time. Why do I skip which value? Uh-huh. No, so you just use the column total and the row total. So this is the observed value, but what we need to get that expected is the row total times the column total divided by the total n. Cool? Awesome. What other questions?
So after, oh, sorry. You can go.
Go ahead, Ace.
Did
All right,
you?
so,
All right, Ace first and then whoever was next. I didn't see who spoke up.
okay. So after we get these numbers, what are we supposed to do with them?
Oh, we'll get there.
Okay.
I know you're just so excited by statistics, but hold your horses. That didn't sound like a genuine laugh.
It wasn't.
Yeah. All right. Let's move on to any other student other than Ace. Whoever just said, who spoke up.
I don't understand why you're doing that for each individual like box.
Because we have to get
Or what exactly?
Yeah, so we have to get the expected frequency. So what is the frequency we would expect based off of our sampling of people, right? And so when you had, let's just say the heads and tails example, we know that our expected frequency is just that 0.5 times n, right? But in this case, for performance, reliability, style, male and female, we don't necessarily have a null hypothesis, right? You can't say that performance, reliability, and style for the two genders we sample here would be equally distributed, right? Because first of all, we have unequal numbers of men and women. We also have unequal numbers of performance, reliability, and style. And so we have to get our expected frequency as a function of these unequal numbers of people.
So the expected frequency, you have to get one for male performance, male reliability, and like that?
Yes, exactly. So our expected frequency for male performance is 16. Our expected frequency for male reliability is 40.
And I'm sorry, how did you get the 16?
So the 16, again, is the row total, so in this case 80, times the column total, in this case 40, divided by the total number of participants we have. So when you add all 6 of these, so 21, 33, 26, 19, 67, 34, when you divide that, or when you add all that up, you get 200. And so you're dividing 80 times 40 by 200, and that's where you get that 16. Does that make sense?
Okay. But wouldn't that just be the same number for everything else? How did you then get like 40 and 24 and like for the rest?
Because those have different column and row totals, right? And so 40 is the column total for performance, 100 is the column total for reliability, 60 for style, and then your row totals, 80 for male and 120 for female.
Oh, okay.
Of course, yeah. So it's always going to be row total times column total divided by n. All right, other questions before we satiate Ace's desire for more stats?
And then all of those denominators added together should equal n, right?
Yes.
Okay, thanks.
Yeah, so these slashes here are just for me to denote. Don't treat these as division, right? Because we're going to do something slightly different moving forward.
Okay.
All right. So, because you're good statisticians, you know you can't just look at differences and say, well, that looks like a big enough difference or it's not. We need to look at probabilities. So to get our degrees of freedom, because we need our degrees of freedom to be able to find our chi-square critical value, just as we had our F critical and our T critical and our Z critical, we have to get our degrees of freedom, which is a function of the number of rows minus 1 plus the number of columns minus 1. Whoops, not plus. Yes, plus. Oh, what am I thinking here? All right, and so we have a number of rows, which in this case is 2. 2 minus 1 plus number of columns, 3. Gives us 1 plus 2, which gives us 3 degrees of freedom. All right, so if we look this up in the back of the book, 3 degrees of freedom for an alpha of 0.05 gives us 7.81.
Did you say it was again? 0.
7.81 for that critical value. So a chi-square statistic is computed to measure the amount of discrepancy between the ideal sample, so those expected frequencies we just calculated, and the actual sample, or those observed frequencies. A large discrepancy in the results, a large discrepancy results in a large value for chi-square. So the bigger the chi-square, the more likely it is that we're going to reject the null hypothesis. And that indicates that the data do not fit the null hypothesis. And the hypothesis should be rejected. So to calculate chi-square, we are summing every cell observed frequency minus the expected frequency squared divided by that expected frequency.
Did you say FO is like the null? I'm sorry.
No, FO is the observed.
Oh, okay.
So frequency observed, frequency expected. All right, so let's go ahead and calculate this chi-square here. What do I do to find the expected frequency for each of these cells? Somebody walk me through what I should do for UAB pass.
You would multiply 160 times 80 and divide it by the total.
Exactly. And the total in this case is 200 again. So let's go ahead and calculate the expected frequencies for each one of these. So 160 times 80 divided by 200, that gives us an expected 64. So let's do UAB failing. So 40 times 80 divided by 200 gives us 16. 89, oops, no, excuse me, 160 times 120 divided by 200 gives us 96. And 40 times 120 divided by 200 gives us 24. All right, so what's the first step? How do we get that chi-square? We can get our degrees of freedom, yes. But how would we actually go about calculating the chi-square value?
You need your frequency observed, right? I don't know if that's like a formula for that. Don't you?
Isn't that what's in
Nope.
the table?
Yeah, so the frequency observed is all in the table already, right? These are those values.
Ah.
All right, so what's next?
You subtract the frequency observed to the estimated frequency.
Yeah, so frequency observed minus that expected frequency. We're going to square that, divided by that frequency expected. We're going to get the sum of all of that. All right, so somebody walk me through the actual numbers. What am I doing?
71 minus 64 squared over 64.
Over 64, exactly, plus, we're doing we'll do, keep it consistent, so 9 minus 16 squared over 16 plus, that around 89 minus 96 squared, squared over 96 plus 31 minus 24 squared over 24. All right, and so when we do that, we get 7 squared is 49 divided by 64, so 49 divided by 64 is 0.77. 9 minus 16 is negative 7 squared is 49. 49 divided by 16 gives us 3.06. 89 minus 96 is, once again, 7 squared, which gives us 49. over 96. Screw that. 0.51 plus 31 minus 24 is 7, squared 49. .04. So when we add all of those up, we get 4 plus 0.51 plus 3.06 plus 0.77 gives us a chi-square of 6.38.
So since you were getting, like 7 times that, was that just kind of, what's the?
That's largely happenstance.
So, but
Yeah.
usually it's gonna be the same number, like 71 minus 47.
No, so you can get a bunch of variety to that.
I didn't know if that was like just random.
No. Well, yes, it is random. Yes.
Okay.
Exactly.
So why did we find the degrees of freedom again?
Degrees of freedom is to find that chi-square critical. So I don't have my book to
Okay.
walk through, but yeah, that would be finding that critical value. So that would allow you to say whether or not that's a significant result.
Thank you.
Mm-hmm.
So if the critical is larger than the actual time, or if the chi-squared is larger than the critical, does that mean we retain it?
Yes, yeah, if the chi-square is bigger than the critical, we retain it. Yep. Awesome, Kenya is on it. So 5.99 is our chi-square critical. So you reject the null hypothesis there.
That label is chi-square critical, just like F critical and T critical.
Yeah, more or less. Correct. Yeah, so Julie, when you look at like this data, so you can see there's a 5-unit difference here and a 5-unit difference here. There's a 7-unit, there's a 2-unit difference here, right? So it's not always the same across, but it's a good question. Here we go. There we are. All right, questions about that? Whoop, somebody chiming in here?
For
Nope.
the goodness of fit one,
Mm-hmm.
are we gonna learn how to do like finish that off?
Yeah, so it's the exact same principle. You just do it for less cells, right? So let's go and find some. We're going to go all the way to the back here just to create some space. All right. So for that goodness of fit, let's say we flipped a coin and it came up heads 73 times. We flipped it 100 times, came up heads 73 times, and it came up tails 27 times. Okay, so we know, let's go ahead and put in our frequencies observed. So in this case, heads, we observed 73 times. For tails, we observed 27 times. Our expected frequency would have been 50 times heads and 50 times tails. And so it's the same principle. Now you're just doing it with less steps here. So it'll be 73 minus 50 squared divided by 50 plus 27 minus 50 squared divided by 50. And in this case, Julie, they will always be the same, right? Because it's just, if you only have two categories, they're all going to be the same distance. But, all right, so 23 squared. Oh, go ahead.
Oh, you're not done? Okay, never mind.
23 times 23, 529 divided by 50 gives us 10.58. And this will give us the same answer, but it's always good to practice just to make sure as a sanity check. 29 divided by 50, 10.58. And so we get 20, nope, we get 21. Let me just actually do it rather than trying to do it in my head. 21.16 for our chi-square. And so this degree of freedom would be the number of columns minus 1. So degrees of freedom would be 1. So I don't know what that critical value is, but if this exceeds that critical value, we would say that there is a significant difference in these values such that this coin seems to come up heads more than we would expect just by chance. So there's probably something screwy with this coin.
All right, thank you.
Mm-hmm. All right. Any other questions at this point? Cool. All right. So when both variables in the chi-square test for independence consist of exactly two categories, such that they form a 2x2 matrix, it's possible to recode those categories as 0 and 1 for each variable, and then compute that correlation. It's going to measure the strength of that relationship. I think I've got data to represent that in a slide or two. Yep, 2 slides. So the value of that phi coefficient, or the squared value, which is equivalent to an r squared, is what we're going to use to measure that effect size. However, when we have two categories for one or both of the variables, when they're more than two, excuse me, then you can measure that effect size using what we call Kramer's V. So the value of V is evaluated much in the same as a correlation. And in this case, we calculate Kramer's V by taking the square root of our chi-squared value. Of our chi-squared value divided by our n, so the number of observations we have total, times df star. So degrees of freedom star. And that star is just to represent this kind of idiosyncrasy wherein we're taking whichever is a smaller value. The rows minus 1 or the columns minus 1. And so here are the standards for small, medium, and large effect sizes, right, for interpretation. Are you Instagramming this? Okay. So for a small, or excuse me, for a DF star of 1, small effect would be at 0.1, medium 0.3, large effect 0.5. And then you can see how that decreases as degrees of freedom increases. All right. Questions about anything we covered today?
Yes,
Yeah.
could you,
Oh, all right. Whoever's on Zoom, go ahead.
yeah, could you go ahead and just briefly explain conceptually why exactly why is there like a negative correlation between the DF and the effect size? Like you said, the larger
Yes.
the DF, the smaller the effect.
Yeah. So it's not necessarily the larger the DF, the smaller the effect. It's that the larger the DF star, the smaller that criterion is, right? And so the interpretation for a test that has a DF star of 3 at 0.06 is the same interpretation as if you had a DF star of 1 with that Kramer's V of 0.1, right? And so what this is conceptually saying is the value you get for Kramer's V is going to have a different interpretation. Excuse me, it's going to have the same interpretation at different levels or different values, right? So this is kind of conceptually the same thing as saying, because we have a moving F critical value, that you can have something that is significant at the 0.05 level with different F values, because your F critical value is inherently reliant on the number of people you have in your study.
Okay, thank you.
Does that make sense?
Yeah.
Okay, cool. All right, Andrew, you have a question? No. So no, so you would not. I would not expect you to memorize this. This is just kind of for your own edification.
Well, I don't understand exactly what DF star is.
So DF star is just to represent the degrees of freedom for whichever is smaller, R minus 1, so the number of rows minus 1, or columns minus 1. So it's just the degrees of freedom, but we represent it DF star because it's not explicit. I mean, it's not the same as the degrees of freedom, right? Because you're going to have a degrees of freedom for that study, but the degrees of freedom star is used specifically for this post hoc test because you're not actually using the real degrees of freedom. What you're using is R minus 1 or C minus 1, or column minus 1. So it's essentially a placeholder to represent a similar concept, but a slightly different calculation. Does that make sense?
So you're only using one of them.
Yes. So if you have 3 rows and 2 columns, your R would be 3, your columns would be 2, 3 minus 1 would give you 2, 2 minus 1 would give you 1. So in this case, your DF star would be based off the columns, which would be 1.
How is that different from a regular degrees of freedom?
Because for the regular degrees of freedom, you're not picking or choosing, right? So it would be R minus 1 plus the C minus 1. So it would not be that you're choosing whichever one's smaller, you'd be adding them up.
Okay, that makes sense. Thank you.
Of course. Other questions?
Did you say you would just add them up? I thought like you would just pick like, 3 minus 1 is 2, so you just like pick like 2 minus 1 because that one is 1 instead.
You would in this case. For your regular degrees of freedom is where you add them up. Not for this.
There's a regular degrees of, but
Yes, so the
No,
df
never
star
mind.
is for Kramer's V, right? The degrees of freedom that you use to find that F critical, or excuse me, that chi-square critical is up here.
oh, okay.
What else?
Thank you.
Of course. What else? Awesome. Well, if that's it, have a good weekend. Enjoy the nice weather today. And I will see you next week.
Did you have Zoom office hours?
I don't, but by appointment. So